I'm Kohei Shimasaki from Hiroshima University, Japan. My presentation title is High-Frame Video-Based Honeybee Activity Sensing using Pixel-Level Short-Time Fourier Transform. Honeybees are the most specialized insect pollinators can transport and store pollen efficiently. They are contributing to many agricultural businesses. For sustainable ecosystems, they are critical for the environmental balance in pollinating flowers or crops, vegetables, and fruits, as well as honey production. Chronic rust disorder is a social problem for significant economic losses in agriculture business. It is a worker bees disappear in a colony. So we need to inspect the timing of CCD and monitor the activity of honeybees. Several studies have analyzed the activities of honeybees inside beehives, such as automatic bee tracking and behavior labeling. To analyze honeybee activities at the beehives, many systems and studies have been reported, such as video-based analysis and sensor-based monitoring and wing frequency analysis. Honeybee counting systems have been developed using RFID chips and a vision-based system. In video-based method, a significant trade-off exists between the measurement area and detection accuracy, because the size of honeybee is dozens of millimeters. However, most of them have handled bee monitoring in a limited narrow area around the beehive. On the while, to recognize high-speed phenomena in the audio frequency range, many high-frame vision systems operating at 1000 fps or higher have been developed. As you can see, upper left video is corresponding to human eyes, and upper right video is corresponding to high frame rate video. Their effectiveness has been demonstrated by object tracking algorithms with appearance-based features, such as face tracking, color histogram, and optical flow. High-frame vision can observe and process high-speed phenomena that cannot be recognized by human eyes. To localize target objects vibrating at a certain frequency at hundreds of hertz without considering their appearances, vibration source localization methods have been developed by executing signal processing for brightness signals at all the pixels. This is our previous work in a dynamic sensing application using high-frame vision. High-frame vision can detect the brightness change vibrating at hundreds of hertz. Thus, the multi-copter propellers are rotating at around 100 hertz. It can be localized at vibration sources with pixel-level digital filters, and our high-frame vision can track the flying multicopter. When we implement this method, we need to know about target frequency beforehand. So there are some programs in our breakthrough. I want to talk about frequency response made by high-frame videos. We can compute time-varying resonance signals for all the pixels from high-frame videos. When we focus on a pixel as a red marker in image, we can obtain periodic brightness changes. After that, we can convert time-varying brightness signals to vibration frequency response. When we focus on a honeybee in this presentation, we can compute frequency spectrum by converting vibration frequency response. If small honeybees could be localized in low-resolution images at a high frame rate, by introducing pixel-level data signal processing to extract pixels around flying honeybees, because their wings are flapping at hundreds of hertz. We could realize honeybee activity sensing through we can monitor the flight activities of numerous honeybees. This will help to quantify the colony health before and after CCD or other serious incidents. This slide shows the flight activity of frequency response using pixel-level STFTs after detection of honeybees and zero-labeled honeybees. If we can compute frequency spectrum from flapping frequency exactly, we can monitor each honeybee's flight activity and the condition of beehive. Our final goal for proposed method is observation of each honeybee's flight activity with high-field vision and these kinds of remote sensing approach without sensors such as RFID tags. This is a pixel-level TFR matching and labeling using high-field vision as I propose. As we use an high-field vision, we can see vibrating frequency at dozens or hundreds of hertz on a pixel. After that, since we apply pixel-level STFTs for all the pixels, we can extract TFR in a pixel, and we can extract multiple vibration regions from similarity image using pixel-level TFR matching and labeling. This is a flowchart of pixel-level TFR matching and labeling. After image acquisition, we compute the STFT image and normalization for all the pixels. Then we can use TFR matching with prepared template TFR. And then we calculate sub-region-based moment features for vibration region. Finally, we can compute connected components labeling with TFR accumulation. After that, we can track multiple honeybee with this method. This is a processing flow for our proposed method after image acquisition. We compute the STFT first. In this case, we need to buffer keyframes for computing STFT. Then we normalize frequency TFR images. Next, we compute TFR similarity with template TFR. Then we extract vibration region and calculate the sub-region-based moment features. After that, we can compute connected components labeling with TFR accumulation. To verify the performance of our algorithm for honeybee activity sensing, we analyzed 1024 by 1024 images captured at 2000 fps with 0.5 exposure time. The target template corresponds to 30 to 250 Hz band. As you can see, light video, honeybee's flapping motion can be seen in high-framed video, so we can compute template frequency response from flapping frequency. This video is corresponding to human eyes. In this case, 1024 by 1024 image correspond to 4 by 4 meter area around the beehive. 1 pixel corresponding to 4 millimeter. It's difficult for human eyes to detect where is the honeybees in an image from a remote place. On the while, our method can realize a multi-object localization using TFR matching even though the targets are very tiny and blurred, because our method can detect pixel-level vibration frequency when there are time-varying brightness changes in a pixel at all the pixels. These videos are corresponding to high-field vision. We can realize multi-object localization and tracking using TFR matching and labeling. These videos show the labeled honeybees. As you can see, we can track the multiple honeybees. These videos are magnified ROI 40 by 40 pixels images of labeled honeybees. Honeybees flapping can be observed using high-field vision. This is a trajectory of flying honeybees out of the scene for 4 seconds. As a result, we can track multiple honeybees flying with our method. when we set K equal 256, frequency accuracy is 7.8 Hertz. Each honeybee's frequency is detected around 160 Hertz. Especially level 3 honeybees flapping frequencies around 220 Hertz for 0.5 to 1 second. Level 6 honeybees flapping frequency is around 250 Hertz, around 0.5 seconds. Generally, each honeybee's peak frequency is detected around 160 Hertz. Finally, this is our conclusion slide. In this presentation, I propose high frame rate vision-based honeybee activity sensing. And then I conducted the tracking experiment for flying honeybees. I verified discriminative ability in the changes in their flight activities. In future works, I want to improve the performance for labeling and tracking. And I will implement multiple vibration source localization on real time. Then I want to classify the different types of insects, such as between wasp and honeybee. I will develop embedded system and long-time monitoring application to count the number of honeybees. Thank you for your kind attention.